Okay, looks like we're up and going. By the way, so this is a brand new laptop I've got, and I'm just going to be double checking things. Okay, so that really looks like it's recording. I feel good that that's bound to be going. Hypothetically, if it turns out that there's something about the new laptop and it wasn't set up correctly and this recording doesn't take, seems like about a 1 chance in 20 at this point. But if that does happen, of course, we do have recordings from previous semesters, so no big. Okay, so back to optimization. You remember we skipped sections 411, 412, and 413 when we were, on our way through the course. We talked about why that was. The idea is we need more time to talk about Chapter 6, and y'all see why now, right? Chapter 6 is chock full of so many ideas, so much that has to get said. Okay, so this is, I'll just remind you, one of the few topics in the book that's not in the prerequisite trail of Chapter 6. So this is one of the few things that I could procrastinate to after Chapter 6, reasonably. Thus giving you more time between when you learn these sophisticated and intricate ideas in Chapter 6 and when you're tested on them, namely this Sunday. So coming up fast. So anyway, so back we go to optimization. I am going to I'm going to skip a lot of the discussions that are in these 3 sections, and let me comment on that. There's a bunch of stuff in these sections that is also not standard material for Math 212 in the semesters. It's supplemental. A lot of the work that I go to, and especially in sections 411 and 412, goes to trying to unify those 2 different algorithms. So the way you find what I'm going to momentarily call interior critical points, and the way that you find boundary critical points. They're different algorithms, but deep down, they're based on the same fundamental idea. So I spent a bunch of time in here discussing sort of, what unites them and, making that all precise. And it's just not something we have time for right now. Okay, so here we go. Skipping all this stuff that you don't need to worry about. By the way, I will, as I have been, I will edit the homework assignment accordingly. Right? There's several exercises in the list of exercises on the syllabus that involve stuff that we're skipping, and I owe you an email if I forget, as I have a record of doing. If I forget to send you an email noting which of these exercises you're no longer responsible for, please don't hesitate to remind me. Okay, so let me start with a reminder about single variable calculus. In single variable calculus, optimization questions look like this. Let's say, let me draw a better curve. Still getting used to this stylus here. Here's a curve. That's the graph of a function defined on this interval here from a to b, let's say. And we can talk about where is the absolute maximum, where are the relative maxima, relative minima, this kind of thing. Okay. And how do we go about doing that? Well, there's a whole procedure. Y'all learned this whole procedure in Calc 1. So, roughly speaking, the idea is you take the derivative, you set it equal to 0, you solve, and you look for what you call your critical points. So there's a common misunderstanding. A lot of students think that when you take the derivative and set it equal to 0, that will find you maxima or minima, one or the other. You'll always get one or the other. And you don't. And fundamentally, it's because that's not what the process is doing. So the process that we use in Calc 1 classes to do optimization is fundamentally a ruling out process. It's a process of elimination. What's really going on is you argue as follows. You say, look, if f prime is not 0, and if f is differentiable, this is what you actually draw a for sure conclusion from. Right? If you're talking about a point, by the way, a point that's in the interior, let's talk about some point x here in the interior. Let me draw that better. Uh-oh. I didn't mean to do that. Sorry. There we go. Okay, at let's say this point here in the interior. At that point in the interior, if the function is differentiable, if the derivative is non-zero, then you can argue directly that this could not possibly be the maximum value of the function because, hey, well, the derivative is non-zero. As I have it drawn here, the derivative is negative. And what that means is if you just take one small little micro step to your left, you're going to find a point where the function is bigger. Now, if you know that somewhere near x, there's a nearby value where the value of the function is bigger than it is at x, then there's no way x is the maximum. Right? So this kind of an argument, you can make that precise. We won't here. This kind of an argument, we can rule out x as being a possible maximizer that we're looking for. Okay, fundamentally a ruling out process. This argument rules out the vast majority of the points in our domain. This rules out all of those points. It rules out all of these points. It rules out all of those points. The only points it does not rule out: this point, because it's not in the interior; this point, because the derivative is equal to 0; this point, because the derivative is equal to 0; and this point, because it's not in the interior. Right? So, yeah, sure, set the derivative equal to 0 and don't forget to check your endpoints, because those are the points that we have not been able to eliminate. We have not been able to rule those out as possible maxima. Not that we have the slightest idea what's necessarily happening at those points, right? In some sense, this is just a leftover after we've analyzed all the other points, right? We've analyzed the points in red. Oh, come on. We've analyzed these points in red here. And the blue ones are the ones that we have given no consideration to. So critical points in single variable calculus, when you say, I've took the derivative, set it equal to 0, and I've remembered to check my endpoints, all these points that you found are points really to which you've actually given no consideration as to whether they're actually maximum or not. Does everybody see what I'm talking about, this process of elimination? It's an important idea. And of course, now you all have seen that, in some cases they are maxima or minima, but in some cases they aren't. I mean, let's not forget, there exist curves that look like this. Right, something like that. Let's go back to this. There, the derivative's equal to 0. My strategy of, hey, I'll try to argue with a linearization argument that there is a nearby point where the function is larger, fails at that point. It doesn't mean it's a maximum or a minimum. It is, in fact, neither a maximum nor a minimum. So when you find... Another way I like to say this: when you find a critical point, what you have found is a point about which you know nothing. Right? So anyway, to keep that in mind, you don't when you put the label critical point on it, it's almost a little disingenuous. It makes it sound like you've drawn a conclusion. This point is itself. There's something intrinsically I know about it. That's actually fundamentally wrong. All you know about it is that you don't know anything about it, and you haven't given it any consideration. Okay, enough of that. All right, so we're going to try to do roughly the same thing in a multivariable context. Now, I'm going to, because of the fact that this is a graph picture, and we're accustomed to looking at graphs, I'm going to start with a graph picture in a multivariable context here. And you see here we have input variables x and y, and we have this output value z. And as usual, so this is how we draw graphs. And, just like we were looking for maxes and mins here, we can talk about looking for maxes and mins here. So in this picture, and I'm not going to make any of these precise definitions, but you can tell, hey, this point here, that's the point we're looking for. That is a relative maximum. This point has the feature that the value of the function at that point is bigger than it is anywhere nearby. Likewise, for this point here. Now, they're just relative maxes. They are not absolute maxes. I mean, the actual biggest value of the function is over here at that point. Right? This is the actual absolute maximizer. And it's on the boundary in this case, as it, per this example that I've written down. Okay, so we want to address the question of how do you find these relative maxes in the interior? How do you find, let me say it a little bit differently. How do we find possible relative maxes and possible relative mins in the interior? And then likewise, how do we find such candidates on the boundary? Right? Now, it's a harder problem for a couple of reasons. For one thing, well, obviously it's multivariable. There's lots of stuff going on. Which derivative do I look at? Is it still true that I just take a derivative and set it equal to 0? Is it that simple? What's the deal with the boundary? Can I just say, like I did in the single variable case, can I just say, oh yeah, just don't forget to check your endpoints? Just, whatever's on the boundary of your interval. The boundary, just always call them critical points. You can't do that in the multivariable context. In the multivariable context, check this out. Here's your boundary. That boundary is a curve. There are infinitely many points there. You can't just say, kind of as an afterthought, just, always check the boundary points because, well, who knows? Right? That you cannot just kind of willy-nilly give yourself an infinite list of points to, check them. We don't have that kind of time. Right? So we're actually going to have two separate discussions here. One, our first discussion is going to be looking in the interior. How will I find candidate? Let me just go ahead and switch to the lingo. How am I going to find critical points, namely points that might conceivably be maxes or mins in the interior? And then a separate discussion is going to be how do I find critical points on the boundary? Or, again, said a little bit differently, how do I eliminate, hopefully, the vast majority of points on the boundary, thus leaving me with only a short list that I can conceivably check of short list candidates of possible maxes. Okay, so two separate discussions. We are going to start with, oh man, it's hard to see the thing on here. There's a little button. There's the button. Okay. We're going to start with the interior. Okay, and we're going to come up with a process that's roughly a process of elimination. Just like we did in single variable calculus, it's a little bit different, appropriate to the context, but there's a process of elimination. Here's the idea. I've talked about that enough. I'm just going to skip to the punchline. This is pretty easy to justify without the details of the argument, and that is if you find a point where the function is differentiable and the gradient is non-zero, there's no way that that's a maximum point. So this is our process of elimination. Okay, now let me explain why. Draw a picture. Now I'm going to switch away from drawing graphs at this point. As you all know, I think graphs they serve their purpose, but they're pretty hard to draw. Right? You take this picture back here. It's a pretty hard picture to draw, and it's hard to get three-dimensional and, visualizing what's going on. It's a lot easier to just draw just the domain. So I'm going to draw just the domain here. And let's consider a point. Let's consider a point such as we just described here. A point where the function is differentiable. This is in the interior. The function's differentiable, and the gradient is non-zero. Okay, well, if that's the case, let's draw that at that point. Here's gradient of f. There's no way that could possibly be a maximum. We're in the interior. Right, that means that from this point, I've got wiggle room in every possible direction. I know what the gradient vector is. The gradient vector points in the direction the function is increasing the fastest. Key point, the function is increasing. It's increasing at a rate indicated by the magnitude of this vector. This is a non-zero vector. That means this has a non-zero magnitude. The function is in the process of increasing as I move in this direction, which I know I can do because I'm in the interior. So, yeah, from this point, take an ever so slight micro step in the direction of the gradient. The function's got a value that's bigger. How could this be a maximum? We know there's bigger values nearby. Yep.
So the theorem says that it's not an unconstrained local maximum. Does that it's also minima or no?
Correct. Yeah. Great question. So I'm focusing all my attention on the question of maxes, just because it gets a little boring to say maxes or mins. But any argument you make about maxes, you can make the analogous argument about mins. Just multiply by minus sign. Yeah, totally. You're exactly right. So it's just for sort of avoiding the tedium that I only say maxima. You're quite right. Okay. So we have here a process of elimination. And here's the great news. This eliminates the overwhelming majority of points in the interior. Almost all the time. It's super powerful. So this one result gives us just tremendous progress in trying to find, candidate maxima or minima. Doesn't always work. There are some points where this fails. There are some points where, for whatever reason, one of these two conditions, this isn't satisfied, and then I can't. I mean, my process of elimination just doesn't work. And those points are points that I know nothing about. Right? I know a lot about this point here. This point right here, definitely not a maximum. I know that it's not, and I know why, because of analysis. The other points, I don't know. It's hard to say. So we call them critical points. And very simply, they're just points where one of the above conditions fails. Either the function fails to be differentiable. Hey, the function fails to be differentiable. We do not have any information about what the gradient vector, if it even exists, might mean. Right? If the function's not differentiable, the gradient doesn't mean squat. Right? Okay. Or, hey, here's another possibility. Maybe the gradient fails to be non-zero, thus giving you a clear direction with a positive magnitude, right? What if the gradient fails to be non-zero? By being zero, right? Well, that's another failure of our argument crashes and burns, and in these cases, I just cannot eliminate the possibility that conceivably, maybe these might be maxima that I'm looking for. So we call them critical points. And put that label on it to give the suggestion that we've actually learned something, which, really in an important point of view, we kind of haven't, because all I know about these points is that they do not succumb to my process of elimination. I know basically nothing about these points, right? But if there's a maximum out there, it's going to have to be one of these because I've already eliminated all the others. Is everybody on board? Everybody see how this is a total rip-off of what we did in Calc 1, as it turns out? It's the same process of elimination. It's even kind of cosmetically similar in that we're taking the derivative and setting it equal to 0. Right? Just don't forget to check where the function fails to be differentiable as well. Okay. Whoops. Again, the buttons on this thing are a little bit different. Okay, so let's apply that to this situation here. Here's a function that's defined on all of R2, and let's see if we can find any critical points, any local maxes, local mins, that kind of thing. And we have a method. We just need to take the derivative and set it equal to 0. Okay, well, wait a minute. Don't forget to check and see where the function might fail to be differentiable. That tends to be a pretty easy thing to do. Notice this is a polynomial. Polynomials are differentiable everywhere. Right? So very often you can dispense with that first obligation. I mean, you're obligated to check for possible points where the function might fail to be differentiable. Those would be critical points. You do have to check and find all the critical points. So this argument has to get said. The good news is that it's usually really easy to say it. Polynomial, always differentiable. Thumbs up. Everybody on board? By the way, this is often overlooked, which is just is too bad. I mean, it's easy money. It's an easy condition to check. It's an easy obligation to satisfy. It's an easy part of the process to demonstrate proficiency with. Just take a look. Confirm that it's differentiable. almost everywhere in almost every case, and you just have to, in some cases you might have to worry about if there's a denominator that's 0, or if there's an absolute value somewhere in your formula, something like that. Most of the time it's really easy to just get those points. Okay, so next let's check and see, where might the gradient equal to 0, because those will give me critical points as well. Okay, well, take this function. Hang on. Take that function. Compute its gradient. There it is. Set it equal to 0. Here, let me do it like this. Setting this equal to 0, we get two equations. That and this. Now, keep in mind, I need for the gradient to be the 0 vector, right? Very importantly, it's the gradient vector being the 0 vector that's what we're worried about, right? If one of the components is 0 but not the other, who cares? If you have a non-zero gradient vector in any sense, you've got a direction and a magnitude, a rate of increase in that direction, and that's definitely not a critical point, right? So you need to have a critical point, you need to have both of the coordinates of the gradient equal to 0. So that's a pretty strong condition to work with. And it gives me both of these equations. And these are easy equations to solve, as it turns out. I wanted to start with an easy example. This clearly gives you x being plus or minus 1. This clearly gives you y equals 0. And having written that down, well, of course, there's only 2 points in the entire plane that satisfy those equations. Okay, so we've just eliminated every point in the entire plane except for these 2. Yeah? Everybody on board? These are the only critical points. These are the only possible local maxes. Everything else couldn't possibly be a local max. Okay. All right, now, what is going on at those points? Well, now, here begins a weird discussion. Here's some possibilities that you might have, these are sort of the obvious possibilities. I mean, maybe we have a maximum, maybe we have a minimum. Those are the ones that we're sort of expecting. But there are several other different possibilities. Here are some of them. What's the word? The categorization, the organization, let me just stick with categorization. There's a better word I'm looking for. I can't quite pull. But keeping track of all the different kinds of possible critical points is much more interesting. And there's infinitely many different possibilities in multivariable calculus. There are no analogies to them in single variable calculus. This is what's called a saddle point. Here you can kind of see why. It looks like a saddle, right? The comment I make every year is that I think this became called a saddle point because at the time this was first discussed, they had not yet invented the Pringle. Right? I think this would be called a Pringle point in modern times. Right? Here's another point. What do you call that? I like to call it a shoulder point. It looks kind of like a shoulder because you have an inflection point in this direction. That way it looks like an inflection point, but cross sections in the other direction are local maxes. This point itself is not a local max because, well, at that point, the value of the function is not the biggest nearby value. Look, there's a higher value right there. So it's not a maximum, it's not a minimum, but it's not a Pringle either. This is a different kind of critical point. So, and there's much more than this. If you ever want to amuse yourself with mathematical weirdness, do an image search on Google for monkey saddle. It's pretty funny. Okay, so how do we deal with this? Let me remind you what we do in Calc 1. We talk about the second derivative test. I want to motivate the second derivative test for you a little bit. Here is the Taylor polynomial. I hope you all remember Taylor series and Taylor polynomials. It's a big deal in Calc 2, of course. This is the second order Taylor polynomial, and as you all hopefully recall, this is the quadratic that best approximates what the function looks like near the point A. If you had to write down a quadratic polynomial that best approximates f at A, this is it. So this has got the same value as f at A. It's got the same derivative as f at A. It's got the same second derivative. In other words, this curve, the graph that is the curve that is the graph of this Taylor polynomial, has the same height, the same slope, and the same concavity. It's mimicking f very well in up to the second order sense near the point A. All right, so let's see what this turns into. If we say we have a critical point. If we have a critical point, then f prime is equal to 0. That means that this whole term goes away, and our second order Taylor polynomial turns into, well, just that. Right, at a critical point, here's your second order Taylor polynomial. And this is an relatively easy thing to analyze. If you look at what's going on here, we have this is clearly a parabola. It's a parabola where we have this constant value. That's just a vertical shift, right? And then we have x minus a quantity squared. That's a parabola who's got a minimum at x equals a. So the vertex, the bottom point of that is at x equals to a. Trying to understand what this curve looks like when x is equal to a is pretty simple. This second order Taylor polynomial, I'm going to say it all comes down to what is this coefficient. If that coefficient is positive, then we have something that looks like this. We have an upward pointing, if you will, parabola. And therefore, at that point, we have a local min. Right, so that's why, or this is a point of view on why if the second derivative is positive, you have a local min. Because if the second derivative is positive, then here's what your second order Taylor polynomial looks like, and it's a local min. Right? It's visually very satisfying. If f double prime is negative, the whole thing flips over, right? You get a downward facing parabola, concave down, they call it. And thus a local max. Okay, so the big idea is, you can take this point of view on how to understand, what's happening at a critical point by thinking about what the second order Taylor polynomial turns into at that critical point. Okay, so we're going to do the same thing now in a multivariable setting. The first thing I have to do is tell you what the second order Taylor polynomial is, and I'm just going to pull this out of thin air. This is the second order Taylor polynomial, as it turns out. This is an exercise I think everyone should do at least once in their lives. It's not that big a deal. But try to persuade yourself that this polynomial actually has the same value as f at a. It has all the same partial derivatives as f at a. And it even has all of the same second order partials as f at a. So this, up to the second order sense, this second order polynomial, this quadratic, is doing the best possible mimic of f at the point A. So second order Taylor polynomial. Anyway, all you got to do is start taking derivatives and confirm that this works out. It's a nice exercise, and I think everyone should do it. Okay. Now, a little bit of commentary. This, you will have noticed, we've never talked about this thing here before. This is called the Hessian Matrix. It's the matrix consisting of all the second partials assembled in kind of what you might call the natural way, sort of just like you would think. So note we do this odd sort of construction with it. We take the Hessian matrix, we multiply by the vector x minus a, and then that result we dot product with x minus a. It's like I'm multiplying by x minus a twice. You're going to want to say x minus a squared. Of course, it's not really, right? But it is multiplying by x minus a twice in two different ways. So it's kind of like, it's analogous, right? And times a half, just like in the single variable case. So it's very analogous result. Anyway, we're going to make a very similar argument, and that is at a critical point. Keep in mind, at a critical point, the gradient is equal to 0. That makes this term go away. all that's left over are these terms, and thus that. So if you want to understand critical points, what you need to do is understand stuff like this. All right, what do this little particular construction, and how can I decide if this is, let me start with naively, how can I decide if this is concave up or concave down? So it's more complicated than that. There's many other possibilities. It's not necessarily just concave up or concave down. We've already kind of seen the pictures. If it was concave up or concave down, we'd always get one or the other of these, and we know we don't. We know that these things are perfectly possible. So there's many different weird possible behaviors of this expression here. This is called a quadratic form. It's a subject discussed in linear algebra. If you take Math 221, you will learn much about quadratic forms. It turns out that there's some really beautiful math that goes into understanding how, this is ultimately, it's sophisticated ideas that have ultimately simple punchlines as to how this behaves. And it's well beyond what we can reasonably do in Math 212. So I'm just going to tell you the answer. The answer is as follows. So this is just something you need to memorize. Again, let me just remind you that it's not analogous to Calc 1. Calc 1, everything works out really nicely and simply. And in a multivariable context, there's more weird things going on. It is actually a pretty sophisticated conversation. So determinant shows up in a way that for which there is no analog in Calc 1, right? And again, if you want to know why, then take Math 221. You will totally see why. We just don't have time here. Not even close. So you do have to pay attention to determinant. And it goes like this. If the determinant is positive, then you get a kind of familiar looking second derivative test. X second partial negative, then you get a maximum. X second partial positive, you get a minimum. It really smacks very strongly of Calc 1. Right? So if the determinant's positive, great news. Now, you may wonder, why is it that it's the second partial with respect to x? Why not the second partial with respect to y? Turns out it doesn't matter. Weird. But anyway, I'm going to cite the theorem just in terms of x, no particular reason. Okay, if the if the determinant is not positive, rather, if the determinant is negative, everything's different. If the determinant's negative, forget about all this, it looks just like the single variable business. It's not. If the determinant's negative, everything changes. The good news is it's simple. And the answer is you get some sort of a saddle point. So something like one of these things. By the way, just a terminology thing, the term saddle point is used specifically for the one that looks like a saddle, but it's also used as a sort of an all-encompassing term for all of these other non-extrema. Shoulder points, monkey saddles. It's a generic term that applies to lots of, again, there's an infinitude of different wacky, weird critical points that you can draw pictures of. So they're all lumped into this term saddle point. So this does not tell you what kind of a saddle point. It just tells you, look, it's not a max and it's not a min. Okay. You will note that these are not an exhaustive collection of conditions. Hey, what if the determinant's equal to 0? Right? There's no comment in the first three conditions if the determinant's 0. What if the determinant's positive, but the second derivative here is 0? Right? No comment from conditions 1, 2, and 3. Cases 1, 2, and 3. So if none of the above conditions holds, then the test fails. And of course, this is kind of like in Calc 1, right? In Calc 1, the second derivative test fails sometimes. Right? Details, y'all remember that. Okay, so why all of this stuff is true, I can't tell you without y'all having taken 221 first, which most of you haven't, so no comment. So I'm just going to assert that this is true. You just need to know that this is true, and that's enough. Okay, so let's see some examples. Here's a function that we considered previously, right? And we've already found the two critical points there and there. Now let's see what can we deduce? Is either one of these a maximum or maybe a minimum, or what do I know? What can I conclude about these points? So let's play the game. Step one, we've got to write down what is the Hessian matrix. That Hessian matrix, and so I got to take some second derivatives. That's just a little bit of calculus. Right? Write down the first partials, write down the second partials, right? Assemble the second partials into a matrix in a sort of naturally organized way. Okay, so there it is. And here's the determinant. It's 12x. Okay, so with that in mind, determinant being 12x, let's analyze these 2 points. We'll start with this point, 1, 0. X equals 1, y equals 0. Plug into that formula. That determinant is 12. That is positive. Right, and that tells me that that these two conditions here apply, and I've just got to decide which of those is relevant here. Well, let's see here. Let's what do I know? I need to know what is the second partial with respect to x. Second partial of f with respect to x at that point. Okay, well, here it is. It's 6x. Don't forget, 6x evaluated at this point, right, where x is equal to 1, y is equal to 0. You got to plug in that point into that second partial, and then at that point, that second partial is 6, which is positive. Thus, local minimum. Everybody on board? Just following through the rules. Okay. All right. Okay, what about this other point? There's this second critical point there. What's the deal? Okay, well, step one, we got to see, what is the Hessian determinant? That turns out to be negative 12. Saddle point. End of conversation. Yeah? Any questions about that? Okay. Sometimes the test does fail. Here's an example of that real quick. So a different function, we haven't looked at this function already, but that function there, you can take the gradient, there you go. There's a critical point at the origin, not hard to confirm, right? Gradient's equal to 0 at the origin. So let's see here. Now, what does the second derivative test tell us? Well, I've got to take the Hessian matrix. Now, so that's more partial derivatives. Write down the partial derivatives, assemble as a matrix. The determinant at the origin, x and y are both equal to 0. The determinant is 0. Well, the determinant being 0, none of the above conditions holds. So the test fails to draw any conclusion. So that, having a 0 here, it does not mean that it's a maximum, does not mean it's a minimum. It does not mean that it's not a maximum. Does not mean that it's not a minimum. Maybe it is. All that we know is that we don't know. Our test fails. We know nothing. Maybe it's a maximum. Maybe it's a minimum. Who knows? Everybody on board? Common misconception, again, that if the test fails, then it can't be any of the listed outcomes, and it's not true. Okay. Okay, there's another example in here that I'm going to skip. This is very supplemental, and it's not at all necessary, but there's a different way to analyze this example where the second derivative test just failed, and you can't actually draw a conclusion, and it turns out that this is a saddle point. Take a look at that at your leisure at some point after the final exam, if you are so inclined, but it's not fair game material, so don't bother with that. Okay. So, what about on the boundary? I'm just skip down to this picture here very quickly. So suppose, and by the way, it's this is slightly more broad than being a boundary, but let's go ahead and consider boundary. So here is a boundary. That's a boundary of a solid in here. So now you'll notice there's 3 independent variables. We've talked about how to find critical points in the interior in there. Right? Take the gradient, set it equal to 0 in that yellow interior there. But what if I'm interested in the boundary? Of all these infinitely many points on that green surface, are there any candidates, possible maxima on that green surface? Going back to the 2-dimensional case, we've talked about how to find critical points in this interior. Take the gradient, set it equal to 0. But we have not addressed what happens on the boundary. Let me just show you why our previous argument, our previous analysis is a total crash and burn. Just doesn't make any sense at all. Let's suppose that I wanted to use my previous analysis and consider the possibility that maybe that might be a maximum. Suppose the gradient of the function I'm interested in is like this. My analysis previously was to say, well, I'm going to eliminate this as a possible maximum by just going in the direction of the gradient and thus saying, hey, there's a nearby point where the function's bigger. But unfortunately, that nearby point that I've just produced is not in my domain. I am not allowed to go in that direction. Right? So the argument of, just go in the direction of the gradient. Function's increasing. Case closed. Nope. Not a valid argument. Right? So we have to take a completely different approach on the boundary. How to deal with the boundary cases. Recognizing that, hey, I might not be allowed to, I can't eliminate just by going in the direction of the gradient. That's telling me to go in a direction that I'm not allowed to go. I'm not allowed to leave the domain. I am not interested in any possible values of the function there. The function's not even defined there. All right. Now, there's, as you'll see, 2 different cases that I've drawn here. I've drawn the case of 2 independent variables. I've drawn the case of 3 independent variables. The arguments are going to be analogous in both. I'm going to consider the case of 3 independent variables because it's a little bit more artistically challenging, and I want to, do the hard one for you. It is different pictures, but very analogous in the 2-dimensional case. I'm going to leave this as an exercise, extending to the 2-dimensional, retracting to the 2-dimensional case. I'm going to leave as an exercise for you all to do on your own. Okay, so now, how are we dealing with this this boundary? By the way, I'm getting ahead of myself. How do we deal with this boundary? There's different ways that you can deal with this. We're going to consider one way, which is to say that we define our surface by an equation. Now, it's not necessarily always how your surface is given to you, right? Granted. But it's really common. I don't want to say usually, but it might be usually the case that this is how you describe surfaces, right? Sometimes it's parameterized, but we're going to consider the case where we have an equation for this surface, right? So that's going to be our assumption. We have this this function. This surface is defined by an equation. That equation, very importantly, involves a certain function. Notice I've got this written here as function equals 0. So very importantly, we are looking at a level set of this function, right? Our surface being described as a level set of some function. That's the context we're going to be interested in. And notice we get a really nice conclusion from that. Because we're looking at our surface as a level set of some function, I know that the gradient of that function is always perpendicular to my surface. Now that's a call back to chapter 4, I guess. Y'all remember that one? Right? Gradients are always perpendicular to level sets. Okay. Now, here's a confusing thing. confusing thing is, well, wait a minute. So what am I trying to maximize? Maximize G? G is always 0. What's going on here? Why is this not a trivial problem? It's a very confusing aspect of these, what we call constrained optimization. Given that we have this constraint, we're constrained to look only at points where G is equal to 0. Is that there's another function that we're actually interested in. The other function is what we call our objective function. Sorry, I'm still getting used to this little pen. Our objective function, the function that we're trying to optimize. So I want to make f as big as possible on this surface, some function f. Right, there is this function f that I don't have in any way represented on this picture. I guess you could say here's f, right? F is some real valued function that I'm trying to make as big as possible, that's defined on this surface. But there's this other function, g, that I use to define the surface itself. And so there's two different functions running around in this question, and you've got to make great efforts to not conflate them. Don't make the mistake of thinking of g as being the thing you're trying to optimize, or f as being the function whose level set defines your surface. It's backwards. There are two separate functions playing different roles in this story, and you've got to make sure to keep them separated in your mind. Okay, so the terminology that I like, very common terminology. The thing we're trying to optimize we call the objective function. The function whose level set gives you the constraint we call the constraint function. All right, is everybody okay with this terminology? We've got two different functions. G's job is to tell us what the constraints are on what values of x, y, and z are we allowed to look at. What is our surface? What is our domain? Where are we? So we call it the constraint function because it gives us the constraint that defines the question. The objective function is the function that we're truly more interested in. That's the one we are actually trying to find the biggest value of. So objective indicating that, our honest objective is to maximize that function. Okay. Everybody cool with the terminology? Okay. So there's our question. By the way, before I go on, another quick comment. Let's think about this this constraint function. Notice the way we've got the problem phrased now. We have this equation, g equals 0. We started off by saying we were interested in looking at the boundary of some solid, but we acknowledge that the boundary of the solid is a surface. Surfaces are described by equations. Equations are a level set of functions. Now that we've got it written as just solutions to some equation, I can kind of expand our charge. Our initial goal was to understand boundaries of solids, but we're going to, in effect, address any optimization problem where our constraint is described by an equation. So, for example, we can open it up now to what if our surface is not even a boundary at all? What if our surface is like a plane that extends infinitely in all directions? That's got an equation. That is some function equals 0, right? Chapter 1. So we started off again thinking about boundaries. We're going to end up solving a harder problem of optimizing on any surface with an equation. Okay. All right. Okay, so I just wanted to throw that out there. Okay, so let's proceed. We've already made our first big observation. The gradient of g, the gradient of our constraint function, sometimes called the constraint gradient for linguistic convenience. It's always perpendicular to our surface, our constraint set. Okay, always perpendicular. Is everybody happy with that? Constraint gradient's always perpendicular to your surface. Okay. All right. Now let's keep that in mind. And now let's set that thought aside and let's go back and let's think about our objective gradient. Here's the gradient of f, let's say. That's what we're trying to optimize. And I've already pointed out that we have this nasty problem of, let's see, we're confined to this domain here. We're confined to this surface. Not allowed to leave that surface. From this point, our previous strategy was, just go in the direction of the objective gradient, but I can't. I'm not allowed to. Right, so how are we going to adapt our argument? Now we're going to adapt our argument I don't want to say obvious, but in a natural way. If I'm not allowed to go that direction because I'm required to stay in the surface. So I'm required to go in a direction defined by this tangent plane. I have to be moving along the surface, and therefore I have to be moving tangent to the surface. Let's do the best possible next best thing, right? If I'm not allowed to go that way, the closest direction to that direction that I'm actually allowed to go is that direction. And that I am allowed to do, right? I mean, here I can explicitly, at that point there, I could move along the following curve. There's a curve in that surface. At that point A, moving along that curve, completely constrained within that surface, I can be moving with that velocity vector, v. So let's just do that instead. That's one of the big ideas. Everybody happy with that? And then you just have to do a calculation. Okay, well, how fast is the function increasing as you're going that way? Well, as I have it drawn here, I mean, it's going to be, here, I'll just write it down. I think I have it written down. Yeah, here we go. Your directional derivative, computed by that, gradient dot v. There's our velocity vector. Here's my little button. Here it is. Old news about dot products. This v vector, if you do the little trig here, compute the magnitude of that v vector, given that this angle is theta and this magnitude here is the magnitude of the gradient. That magnitude is magnitude of the gradient times cosine theta. And so you plug this in. Magnitude of v is computed by that little trig, and there's our directional derivative. It's magnitude of the gradient squared times cosine squared theta. And good news, for the vast majority of points in our domain, this is positive. Therefore, the function's increasing. As I move along that perfectly allowed curve in the surface, that my function is in the process of increasing. Therefore, I'm not at a maximum, and I can eliminate that point. Everybody see how that works? Any questions? Okay, so this is the basis of all the ideas of that we're going to talk about of constrained optimization. And now, again, just like with the single variable case and just like with the interior case that we talked about a few minutes ago, all we have to do is figure out, where does this process of elimination fail, right? What are the assumptions that go into saying, and therefore this can't be a maximum? Well, I did this calculation. When might this calculation fail? Well, there's a couple of ways this calculation might fail. You'll notice I cited this formula. That requires that f is differentiable. Right? I mean, it's better be different. If f is not differentiable, then my directional derivative calculation is bogus. The argument crashes and burns. So I need differentiability for that to work. I need for that to not be 0, right? If the gradient vector were 0, then I don't conclude the function's increasing. I conclude the directional derivative is 0, which means I haven't got the slightest idea what's going on in terms of, are those nearby points second order slightly larger or second order slightly smaller? I don't know, right? So if the gradient's 0, the argument fails. So for this argument to work, I need for the gradient to be non-zero. Lastly, this angle here. And let's think about that angle. I need the cosine of that angle to not be zero. Right? If cosine theta is 0, then again, my directional derivative is 0. I know nothing. I can't eliminate it. Argument fails. Okay, so now what does that tell you about the angle? If I need the cosine, I mean, when is the cosine equal to 0? Well, cosine is 0 when theta is pi over 2, namely when theta is a right angle. So if this angle here were a right angle, we would have this picture where the gradient of f perpendicular to the surface. Right, so I need to have the gradient of f not perpendicular to the surface in order for my process of elimination to work. Everybody see what happened there? So it's all over, but just a couple of details. I mean, this is my process of elimination. It works the vast majority of the time. Critical points are going to be points where, well, my process of elimination fails. And when is this process of elimination going to fail? It's going to fail when one of these conditions fails. So let's just enumerate the 3 different ways that these conditions can fail. These conditions could fail by the function not being differentiable. Could fail by the gradient of f not being non-zero. Right? Double negatives are funny. And it could fail by the gradient not being not perpendicular to the surface. Right? Okay, so you've got to think through the double negatives. So said differently, our critical points are functions, are points where the function fails to be differentiable, where the gradient of f is 0, or where the gradient of f is perpendicular. If any one of these 3 things happens, the process of elimination fails. I have no idea what's going on if any of these things happens. So I'm going to call those critical points and think about them later. We'll check them later. Okay, is everybody happy? Any questions on this argument? Now, there's a little twist here. That you could call these your theorem and go on with it and just, this is how you find critical points. But there's something really undesirable about this. How do you check this? How do you check if a vector is perpendicular to a surface? We don't really have algebra for that exactly. So that's annoying. So we go back to, let me remind you, one of our earliest conclusions here. The gradient of g is always perpendicular to the surface. Right? If the gradient of g is always perpendicular to the surface, and I want to know when the gradient of f might be perpendicular to the surface, right? I want to know when gradient of f is perpendicular to the surface. I know that gradient of g is always perpendicular to the surface. Well, what I'm looking for is when is the gradient of f also perpendicular to the surface, also in addition to gradient g. Let me say that differently. When is the gradient of f pointing in the same direction as the gradient of g? When is the gradient of f a multiple of the gradient of g? Yeah? Everybody see that? It's just a sort of it's a different way of saying approximately the same thing, but something that I can write down algebraically. And so there you go. Instead of saying gradient of f perpendicular to the surface, we're going to say gradient of f a multiple of, parallel to, the constraint gradient. Now, those of you who are eagle-eyed might have noticed something else that's happened here. And let's see if I can get this on the page at the same time. Let's see here. Oh, it's not going to fit at the same time. Okay, anyway. Previously, we wrote down gradient of f equals 0. Now I've written down gradient of g equal to 0. What's up with that? I just changed the g the f to the g. Can you do that? Is that legal? So it's actually a fairly detailed little discussion. So let me just walk you through it very, very quickly. We're interested in when the gradient of f is equal to 0. Here's the good news. Condition 3 already catches that. If the gradient of f is equal to 0, the gradient of f, being the 0 vector, will be a multiple of the gradient of g. It'll be 0 times the gradient of g. So I can really just kind of throw this away now that I've written this multiplier equation. There's just, multiple of gradient of g, multiple of one vector that gives you the other vector. Having written that down, I don't need to write this gradient of f being 0 anymore at all. I can just toss it. So I didn't change it. I threw it away. So then you ask, well, then why do we have to include gradient of g being 0? Why is that something I need to worry about? Well, it's a little bit annoying, but when I drew this picture, I made an unfair assumption that does not always hold. Right? I drew the gradient of g as a non-zero vector. What I'm really interested in is when is the gradient of f perpendicular to the surface? Right? When is the gradient of f perpendicular to the surface? That's what I want to get my hands on. If the gradient of g is non-zero, then yeah, one's a multiple of the other. But what about this scenario where the gradient of g is just a 0 vector? If the gradient of g is the 0 vector, then it could be that the gradient of f is perpendicular to the surface. Something I'm very interested in. This would be a critical point. My process of elimination fails. I need to know where this happens. And yet the gradient of f is not a multiple of the gradient of g. Gradient of g is 0. No non-zero vector is a multiple of the 0 vector, right? So there's this little annoyance when you translate this statement about, the geometric statement of perpendicular to a surface. When you translate that into the much easier to work with algebraic equation, you're liable for the possibility that this actually might not tell you what you want. When this is 0, you don't get what you want. So you've got to throw that in as an additional condition that you're worried about. Whenever the gradient of g is equal to 0, your test stinks, right? This does not tell you what you want to know, and so you can't eliminate those as possible maxes. Okay. So anyway, that's the argument. It's nice punchline, though. You have 3 conditions to check. If you want to find a critical point on a constraint set, check to see if the function ever fails to be differentiable. Check to see if your constraint gradient is ever 0. Check to see if this little equation right here ever happens, and off you go. Okay, a little bit of terminology. For reasons that I can't go into here, this is called the degeneracy condition. Very briefly, let me just say that when the gradient of your constraint function is 0, what that means is that not only does this problem that I described come up, but it turns out it also means that your surface might have something really wrong, really perverse, something strange. Your surface might not be a nice, smooth, flat surface like we drew in this picture. And that's a much more sophisticated discussion I can't go into. But in such a case, when the surface is not a nice, flat, smooth, pretty, normal-looking thing, we call that a degenerate point on the surface. So this condition here is called the degeneracy condition for that reason. So I'll be using that terminology a lot, and I encourage y'all as well. This condition has a name as well. So, by the way, you may have noticed this theorem is called the Lagrange multiplier theorem. Sometimes it's called the method of Lagrange multipliers. So this condition, the one that usually gives you the points that you're looking for, it's called the Lagrange condition. And by the way, in case you hadn't figured it out already, this thing that you multiply by one vector to get the other vector is called the multiplier. So it's a little bit of terminology. Okay. Okay, how are we doing so far? Is everybody on board? Everybody see where all these conditions come from? Okay, cool. Oh, again, with the, where's the thing? Okay, here it is. Wow, that's weird. Okay. So, let's see an example. So I want to find critical points of this function. Here's our objective function. Now, before I finish reading the question, let me point out that this function has a smallest value. The smallest value is 0. Right? That was easy. So don't oversimplify your question. It's tempting to say, smallest value is 0. What's the biggest value of this function? There is no biggest value. Right? Easy to see. Okay, but that's not our question. The question says what we want to understand is critical points, so candidate biggest values, candidate smallest values, for this function on the domain that's defined by that equation. So on a constraint set, do I have a picture of this? Yeah, here we go. So I've got this constraint set. It's on this plane that I want to know what are the critical points of this function. So where might this function be the biggest? Where might it be the smallest? Now, it's not hard to persuade yourself. This plane does not go through the origin. So even though f, independent of a constraint, could be 0, the actual smallest value of this function in the problem that we're interested in is not 0. Right? On this plane, there's f can get kind of small. We can get kind of close to the origin, but we can't get there, and so the function can't be 0, and we have a hard problem on our hands of how do we actually find, on this constraint set, what's the smallest value of this function. Everybody see where there's a hard problem, relatively? I mean, by the way, I know there's a geometric solution to this problem. There usually isn't. I wanted to start with an example that's easy, algebraically easy, not because I wanted to have a geometric solution. I want to just keep the algebra from getting out of hand. So there's our problem. We have a constrained optimization problem. Subject to this constraint, I want to find critical points of this objective. Okay, so we have a process. Here it is. Lagrange multiplier theorem. Check and see where the function fails to be differentiable. That's the objective function. Where does f fail to be differentiable? Oh, well, that's easy. The function's a polynomial. It never fails to be differentiable. So, cool, right? No, there's no differentiability critical points. Okay. Next. Are there any degenerate critical points? Are there any points where the constraint gradient's equal to 0? You got to check this. If the constraint gradient's equal to 0, who knows? We cannot eliminate that as a possible maximum. It might be a maximum. We have to call it a critical point. So you got to check for it. Okay, well, here's our constraint gradient. For what values of x, y, and z is this equal to 0? Good news. 6 is never 0. Right? An instructor of mine one time made a joke about how, you can't talk about, sufficiently small values of 6. Right? 6 is 6. It's never 0, period. Right? So there's again, there's no critical points. So there's no degenerate critical points. The degeneracy condition is never satisfied. Okay, so hey, we're 2 out of 3. That's good. Right? We found that there are no differentiability critical points. There are no degenerate critical points. And now we move on. Are there any Lagrange critical points? Are there any points that satisfy the Lagrange condition? Here's where the algebra gets a little hairier. So this function f, there's its gradient. That's our objective gradient. This function g, the function By the way, you got to think about how does the constraint equation, how can you rewrite that as a function equaling a constant? I could have just used this as my constraint function because 49 is a constant. That does give you a level set. The arguments all work just fine. Just as a matter of superstition, I guess you might say, I don't know. I tend to like to subtract it over, and just so I always have something equals 0. You don't have to do that. It doesn't matter. If it makes you feel better, you can. It's not going to make any difference at all. So this function, previously noted, the constraint gradient is 632, and so our Lagrange equation looks like this. We want to look for possible solutions to this equation, and this is a hard algebra problem. You might have noticed we haven't done these kinds of algebra problems before. It's like a vector algebra problem. Right? So, it's not that bad to do them. Just notice first that a vector equation is equivalent to several scalar equations. I need all the coordinates to be equal if the vectors are going to be equal. So I have these three equations here. There's a temptation to just look for any possible solutions to those equations, but let me just remind you of one thing. We are looking on our constraint set, right? I'm only interested in finding critical points on this set, right? If I find some point, I don't know, way up here that happens to satisfy the Lagrange condition, who cares? It's not on our constraint set. I could not care less if a point that I'm not allowed to think about satisfies a condition that's relevant only to points on the constraint set. So in fact, don't forget this is a big deal. Very, very often students forget this, but you don't just write down the Lagrange conditions by themselves. You write down the Lagrange conditions and the constraint, right? So it's the four of these equations together that you want to find solutions to, right? And now notice we have 4 equations and 4 unknowns. That's good. That's it's all balanced off, and it's a matter of doing a little bit of algebra. Now, here's the bad news: how the algebra works out on these questions, not always the same. And there's issues that can come up. What I'm going to show you is the way that usually work. This should definitely be your first thing to try, and that is, if I can find a little eraser, eliminate lambda. And by eliminate, what I mean is solve for it in all 3 of those equations and then set the resulting things equal to each other. So notice in here, if you solve for lambda in those first 3 equations, lambda's got to be 2x over 6, it's got to be 2y over 3, it's got to be 2z over 2. All of those things have to equal to lambda, therefore they have to all equal to each other. And now you can forget about the fact that you got those equations by having solved for lambda. Now you have equations in which you have eliminated lambda. So standard little algebraic trick. If you do that, stuff tends to fall into place. In this case, you could solve in these equations for y and z in terms of x. Plug those into your constraint equation. Remember, this was our original constraint equation. If you know y in terms of x and z in terms of x, you plug in and you get a big equation involving x. Therefore, you solve for x. And therefore, you've solved for y and z. So, eliminate lambda. And then, do what you got to do. Don't forget your constraint equation and go through and solve and see what you can find. Okay. I want to show you one last one, just because the algebra works out in an interesting way, and I'm going to go fairly quickly through this because I see we are very short on time. I have 1 minute. Okay, so let me just go straight down to the Lagrange equation. There's no degenerate critical points, no differentiability critical points. Here's your Lagrange equation. Here's the 3 corresponding equations. A lot of students will throw up their hands upon seeing this and say, there's I don't know, I've tried to make it with a frowny face or a smiley face, but a lot of students would say, hey, there's no solutions there because look, lambda would have to equal to 1, but it would also have to equal to a 4th, it would also have to equal to a 9th. Lambda cannot simultaneously be 3 different values. Therefore, no critical points, we walk away. And that's completely wrong. This is an example of a very dangerous little landmine that they don't make you step on and learn from hard knocks as much as they should in high schools. What you've inadvertently done there is divided by 0. Right? This does not mean lambda equals 1. This means lambda is either equal to 1 or maybe x is 0. If x is 0, then lambda is under no obligation to be 1. Right? So there is no contradiction of the sort that seems to be suggested by these equations. So you can deal with this by considering certain cases. Let's suppose, just so that we can have something to work with, let's suppose x is not 0, hypothetically. If x is not 0, well, okay, then I know lambda is 1. I can plug that into these two equations. If lambda is 1, that tells me that y and z are 0. If I know that y and z are 0, put that into your constraint equation. If y and z are 0, x is plus or minus 6. And so you get these two critical points that you would have otherwise totally missed. Now notice, that was just one case that we considered. We considered hypothetically, no particular reason, what if x is not 0? Well, what if y is not 0? If y is not 0, then you can solve for lambda. You can plug that lambda into these equations. X and z have to be 0. Plug into the constraint. You get these 2 points, etc. So grand total, you're going to get 6 critical points if you're careful. So heads up, right? Be real careful. It's tempting to see the daylight you look at that and you're like, contradiction, no lambdas, no critical points, yay! But as you run toward that daylight, you step on the landmine and you lose. Right? So make sure that you're careful with that. Don't inadvertently divide by 0 and miss critical points. Yeah, everybody happy? Okay, all right. We are done. Let me just point out that this 2 constraint critical points very often not included in the semester discussions. Likewise, section 413, very often, in fact, usually, this is not part of the semester math 212. So, I'm sad that we didn't get to it. I think it's cool material, but it's usually not covered anyway. So it's supplemental material that we did not get to include. So we did finish. We made it, and we are done. Now I do have one announcement for y'all. I did totally forget something important, and that is I forgot to leave 10 minutes or whatever. For y'all to complete course evaluations. I'm sorry, it totally slipped my mind. I'm going to ask y'all if you would. Normally we set aside class time to do this so that students will, for lack of anything better to do, go ahead and do it, right? But anyway, if you could take a few minutes, it's very important to the math department. It's very good for me, but more important to the math department for there to be a high return rate in the course evaluation. So if you could take a few minutes, click through. Shouldn't take you very long. Much appreciated. You can do that anytime. I think anytime before the final exam, if I understand correctly. Okay. All right. See y'all later. Oh, and I have homeworks to return and attendance to take.